Yeah, so what we discussed in the last class about, we discussed about quantum numbers, like first we discussed de Broglie hypothesis, then next Heisenberg's uncertainty principle, related questions, then next we discussed quantum numbers. Okay, so during the discussion of quantum numbers I have told you that, so Schrodinger wave equation we have, so upon solving that Schrodinger wave equation we got three set of numbers which we are calling it as principal quantum number, azimuthal quantum number and magnetic quantum number. So this is a like Schrodinger wave equation. Okay, so these, upon solving this, see here they have indicated something called psi. So what do we mean by psi here? It's a wave function. Okay, this is a reduced form, you can say like h psi equals to E psi. They will ask which are the following is a Schrodinger wave equation. So these two equations you need to remember. So you can just remember dou square psi by dou x square plus dou square psi by dou y square. So dou square psi by dou z square plus 8 pi square m by h square E minus v. E means total energy, v means potential energy, multiplied with this wave function. So wave function is to indicate the electron. Okay, like finding an electron is indicated with wave function. So now in order to consider, see, upon solving that Schrodinger wave equation we will get some solutions for that. Okay, so we will get solutions for that. So we will get many different solutions, but only few set of solutions are accepted. So like only those solutions are accepted where we are finding this wave function now. So if that wave function, whatever the solution we are getting, if that wave function is continuous, then we can accept that. Okay, and it should be have finite values. Okay, must be, wave function must be finite. Continuous means, for example, I am indicating a wave like this. This is a wave. Okay, it is a full wave now. Okay, now if I indicate the wave something like this, something like this. See, this is a discontinuous now. So wave function must be continuous and it should be finite and it should be what? Single valued. Must be single valued. Okay, first derivative of wave function must be continuous. So these 4 points they will give in the options to identify what are the conditions to be satisfied in order to accept a solution of wave function from the Schrodinger equation. Okay, so these 4 like that sentences are important here. And the next, so what I told you, so for finding, for example, I have an electron at here. Okay, so which I am representing with a distance r from here. So we have in the sphere, just imagine three-dimensional space where we have electron at one point. So you like take the origin from the nucleus, so it will be at a distance r. Okay, so in the x, y, z coordinates we have 3 coordinates like x, y, z coordinates. Okay, this is what spherical polar coordinates will say. Okay, so now using this we will be finding the electron where it is. Okay, so for that we have x, y, z coordinate now. So in spherical polar coordinates we will be taking like this. It means we have 3 parts. One is radial part. Okay, I mean one is radial part, another one is angular part. These are 2 parts we have. One is radial part I am saying, another one is angular part. In this angular part again we have 2 parts. One is theta part, another one is pi part. Okay, so what is the use of studying this? See, radial part will give some quantum number. See what I told you, one radial part, one angular, like angular part again have theta part and pi part. So from this radial part we can able to get the quantum numbers like n and l. So n, l are coming from which part of the wave function? Radial part. Okay, and angular part is giving what? L and mn. So you can expect, so radial part, by solving the equation from radial part we will get what? N and L. N means what? Principal quantum number and L means azimuthal quantum, like angular quantum number or azimuthal quantum number you can say. Okay, these two comes from where? Radial part, and angular part gives L and ml. So L value is coming from both of them, but n is coming only from radial part and ml is coming from angular part. Okay, L is common in both. Okay, remember this. Okay, yeah. So solving equation is not needed, but just remembering that points are important here. Okay, so now what do we mean by orbital? So orbital is a 3-dimensional space okay, around the nucleus where probability of finding electron is maximum. Okay, so yeah, so 3-dimensional space around the nucleus where probability of finding electron is maximum. So what is an orbital defines? It's probability of finding an electron it defined. Okay, so it does not define path of the electron, but it defines finding an electron will be maximum. That is what defined here. Okay, and next here, next we have 4 set of quantum numbers that we have discussed, and we also solved related questions. So we'll be revising the same thing using few important like previous year questions. So tell me here the 4 set of quantum numbers for electrons in the outermost orbital of potassium. Okay, what is the atomic number of potassium? 19. Now we'll also look into the electronic configuration also, but tell me, do you know what is like how can you write electronic configuration for this? 19 means which orbital it is or which shell it is, or tell me in the periodic table potassium belongs to which group? First group. Okay, first group, and atomic number is 19. So first group means 18th, after 18th is argon right now. So after that we have potassium. Okay, so 19th here. So what is what is the electronic configuration you are writing for this? So it will be like 3s2 3p6. This is a valence electronic configuration. Then here it will be 4s. I will tell you this electronic configuration also after some time. So now 4s means what is the n value here we have? 4. N equals to 4. Okay, n equals to 4 you are saying. What is the L value for s orbital? 0. And what about ml value? ml lies from minus L to plus L. So 0 only. Next, spin is how much? ms. So plus half. Okay, you can take plus half. So where do we have? So that will be our answer. Okay, simple. Next, answer these questions fast. If you answer, then we will move forward with the other topics from the chapter. So compare the energies of following set of quantum numbers for multi-electron system. Tell me fast. What I told you in the last class, for multi-electron system, energy depends on what? N plus L, and the next one is N. Okay, first look at the N plus L value. If that is equal, look for the N value. So look at here, the first option. In the first option, they have given N equals to 4, L equals to 1. So total is 5, and here 6, and here 4, here 5. So which is bigger number here? This is bigger. So I can say, and here it is 4. Okay. So which is highest number here? B. Where do we have that B is more here? Here we have, and where do we have other than that? Fourth option. Okay. Okay, here. Next, after that here and here, but N value is greater now, so this will be. So after B, A, okay, here only, and the next second option also here we have. Okay, after that 6 there, over 5 over. After this one D here we have, here also we have. After that 4 and 4, but higher N value I told now, so
4 option
E. So option 4 is perfect. Okay, is that clear? Okay, try to look at the all the options easy, like carefully, because you should not lose the marks. Yeah, tell me.
values cannot be same.
No, it cannot be same. If N plus L values are same, then you can look for the N value. Sometimes N values are also same, but N plus L value will be different. That's what, first you look for the N plus L. So this rule is called Bohr-Bury rule. Bohr-Bury rule. So Bohr-Bury rule is to give the energy order of energies of the orbitals. Okay, next question. Maximum number of electrons that can be accommodated in a shell with N equals to 4. Maximum number of electrons that can be accommodated in a shell with N equals to 4. How do you solve this? So in a shell, N value is 4, they are saying, N equals to 4. Okay, so for given 4, What are the L values possible? 0, 1, 2, 3, right now. So you can get S, again P, D and F you can get. Okay, so in S orbital, like I can write 4s, 4p, 4d and 4f. Okay, directly I will give the formula. Yesterday only I given, but I think you have forgot. In that case you should follow this thing. Okay, so in like 4s it is only one orbital now. So 4p, p orbitals are how many? L value is 1 means 2l plus 1, 3 boxes, like 3 boxes you are writing now. So 3 orbitals, and these are 5 orbitals. Okay, so 5, and these are 7. 7. Okay, so 7, see, 1 total orbitals are how many now? See, so just use n square. N square is 4 square, so you will get 16. So just check 16 orbitals are there or not here. 16 are there? Yeah. So 16, each orbital can accommodate how many electrons? 2 electrons with opposite spins like this. So you just use 2n square. So 2 into 14 square, 6, so 4 square, 16. So 32 electrons you can fill maximum. Is that clear? So if they ask in a particular energy level or in a shell, how many orbitals are possible? Just what is the formula? N square. Orbitals possible are n square. Maximum number of electrons possible is 2n square, because in each orbital 2 electrons, so 2n square. So they are asking maximum number of electrons. Okay, so 32 here we have B. Okay, is that clear or not? Yeah. Next question. Arrange the following orbitals in the decreasing order of energy. Which is highest? This one you are saying? Okay. So here 5 here, just take n plus L value, 4 here and 3 here and 4 here. So capital D is highest, and the next B, C, A. So where do we have? B, D, C, A, option 2 over? Yeah. Next. Tell me answer for this. Which of the following set of quantum numbers is not possible? Okay, how will you answer this? Which of the following set of quantum numbers are not possible? Okay, we will come back to this once after studying 3 rules, so that you will get more clarity, like Hofbauer principle and Hund's rule and Pauli's exclusion principle. Just tell me for this. This one. Maximum, the quantum numbers for 4 electrons are given below. Tell me correct decreasing order. Energies. Fast.
1, 3, 2, 4.
Where do we have? See, here it is again 6, 5, 5, 4. So 6, 1, next 1, 3, 2, 4. Second option. Tell me for this, which of the following orbital does not exist? Does not exist. More than one option also correct only. So do we have 3s? Yes, n can be 3, L can be from 0, 1, 2. Okay, so 0 is there means s orbital is possible. Okay, s subshell is possible. Next 3f they are saying. N value is 3 and L should be 0, 1, 2 only. But here f, for f what is the L value? 3, which is not possible here right now. Next one, 3f is not possible, and what about 2d? That is also not possible because L value is 2. Okay, and next 1f is also not possible. These 3 are does not exist, only 3s will exist. Okay, next. So tell me about these two. I think above one you can able to answer, but this one you tell me from Bohr's model. Transition. Which are the following series of transition in the spectrum of hydrogen atom falls in visible region? Balmer series. Okay, just give me quick revision. Lyman appears in UV and Balmer visible. Next two, both are IR only. Okay. Okay. So these questions we already solved, and tell me for about this one particularly. Arrange them. N gives what is the use of n? Principal quantum number n. Size of the orbital. So if you want, what is the radius formula? Rn equals to 0.529 n square by z you are writing. So greater the n value, greater is the size. Okay. So n gives size of the orbitals or energy also.
L shape of orbital.
L gives
Shape of orbital.
next ml
B ms give
spin of
orientation of spin of electron.
orientation of spin of electron, and this will be,
Orientation of orbital.
that's it. Okay, yeah, whatever you can choose there. Okay, next, and these things we will be solving today. So before that you need to know few more things here. This kind of questions are there. So in order to understand, look at here, what is the difference between orbit and orbital? So orbit is a well defined circular path. It means you can say two-dimensional thing, circular path, in a circle you can say, around the nucleus where electrons revolve. So maximum number of electrons in an nth orbit is, just now we have used 2n square, 32 answer we got now for one question. Yeah. Next, orbital means this is a three-dimensional region around the nucleus where electrons are most likely to be found, maximum probability. Okay, this is what? Sphere. You can remember this as a sphere, this as a circle. Okay, next. So cannot accommodate more than 2 electron. Orbital cannot accommodate more than 2 electron. Always remember, orbital can have maximum of 2 electron. So for orbit you can use 2n square. Okay, next. Here we have the different shapes of orbitals. We have studied while studying about angular quantum number like n. So L if is equals to 0, we are saying s orbital which is spherical in shape. If L equals to 1, we are saying p orbital having dumbbell shape, and this will be 2 means you are saying double dumbbell shape, like that right now. So now look at here. So now if I say 1s orbital, okay, so 1s is nothing but if this is a nucleus, if this is a nucleus, red color mark, so around we have the electron probability, maximum probability of finding electron, we are saying orbital means. So 1s orbital will be very close to the nucleus. Now why I am saying very close to the nucleus? Nucleus is positive charge, electrons negative. It means that electrons will be very closely related, revolving around the nucleus. It means the probability of finding electron near to the nucleus will be maximum in case of 1s. Yes or no? So it means this dot, whatever you are seeing here in this pictorial representation, see, it will be looks like this. This red, like white, whatever the color you are seeing, violet color, that is indicating probability of finding electron is maximum, okay, near the nucleus. And here you can see this is for what? 1s. And if you see for 2s, you have something like around the nucleus with this, and there is some space. After that again you have the orbital representation. This is for 2s. See, between the nucleus and the 2s orbital you have some space here. So that space is called a node. What is that? Node. Node means
Space between two orbitals.
probability of finding electron is 0. So do we have any probability of finding electron in this region? 0. Okay, so node is a place or the region, probability of finding electron is 0. So how many nodes are there for 2s orbital, they will ask. So there will be one node here. I will tell you how to find that. And if you look at for 3s, so there will be 2 nodes. Where do we have that? After crossing 1s orbital, between 1s and 2s one node, and between 2s and 3s another node. So total two nodes are there. Like that you can understand here. Okay, so now we have two types of nodes. One is, so nodes are two types I am saying. One is radial node and other one is angular node. Okay, radial node and angular node. In order to find radial nodes, you just use this formula using quantum numbers. N minus L minus 1 gives what? Number of radial nodes. And angular nodes just use L. Angular nodes are equals to L. Okay, so now if I ask total number of nodes means add these two, radial nodes plus angular nodes. Radial nodes are how many? Total nodes equals to radial nodes plus angular nodes. Radial nodes are N minus L minus 1 plus L. So it means minus L plus L removed. So you will get total nodes is N minus 1. That's it. Okay. So now look at here. For 1 is 2s we will say. So I am saying 2s orbital. How many radial nodes are there?
2s orbitals.
Radial nodes, how many are there? 2s. Just use this formula. N value is how much? 2. And for s, what is the L value? 0. Minus 1. So radial nodes are 1. So here you got one node now. What is that node? That is radial node. Okay. And how many angular nodes for s orbital? What I told you, angular nodes are equals to, just equals to its angular quantum number L. So what is the L value for s? 0. So therefore angular nodes will be 0. Always whatever the orbital, 3s, 4s, 4s I told you, or 2s I told you, 1s, whatever it is its angular nodes are 0 in case of s orbital. In case of p, 1. Angular nodes are 1. Okay. So now I am saying how many angular nodes and radial nodes for 3p. You tell me. Radial nodes you tell me first. N is 3 and L is
0,
PP. L is for P, N minus L minus 1. L is how much for P? 1 minus 1. So how much it is? Minus 2 means it will be 1. Radial nodes are 1. Angular nodes? Angular nodes also 1. Total nodes? N minus L, N minus 1. So 3 minus 1, that is 2. Just add these two numbers. 1 plus 1. Okay. So you can use this. Is that clear or not? Yes. Okay. So now we have some graphs to represent these orbitals. Like what is a graph that represent 1s orbital there, or what is a graph represent for 2s here in the given options. Okay. Like that we have. So just look at here. Okay. So here what I discussed for 1s orbital, we have nucleus here. The probability of finding electron will be maximum around the nucleus or very close to the nucleus in case of 1s. Right now, it means if I say psi is the probability, like electron distribution I am saying, and here we have r, it means radius. So if this is the nucleus, so very close to the nucleus we have maximum electron density in case of 1s. Okay. So it means this, that's why this graph is maximum at starting. It means very close to the nucleus. As distance increases, what happens to the electron density? Decreases, because it is more close to the nucleus. So at the beginning it will be maximum and it will be decreasing like this. Is that clear? Okay. See, for example, I have psi equals to minus 1. Okay. Now if I want to do psi square, what you will say? Minus 1 square will be?
plus 1.
Always it will be plus 1. So why I am saying this basic one is, see, for 2s how many radial nodes you got?
2s.
How many you got radial nodes? 2 minus 0 minus 1. So 1 radial node you got. So it means the graph will look something like this. Starts from here, reaches here, after reaching it will goes like this. It means what? See, how many times it is touching this x-axis?
2.
Starting and ending, beginning and ending point you remove. In between how many times it is touching? So it represents one node. How many times it is touching? So it is starting from maxima and going here, and this represents what? one radial node. Here we have seen that white gap. Okay, so this is what the indication. So this graph is for which orbital? 2s. One radial node you have, so this is for 2s. Okay, now if I want psi 2s square graph, how you will draw?
Psi 2s square.
This is probability density graph. Probability density graph we will say. So tell me, just that's why I told you here, psi means -1, psi square means always it will be +1. So it means, see, for a graph it is representing plus and this is minus if I say, so it will be something like this. Reaches here, again goes like this. For this understanding I have given that. So both will be positive. So now what is this? Node, one node, right now. So this is also indicating what? Which orbital it is? 2s. Okay. So now we have, this is probability density. Okay. Next we have probability distribution curve. What I am saying, one more? Probability distribution. It means what is this probability density, probability distribution? See, if we have a nucleus here, okay, this is a space around the nucleus. From this nucleus at a point R, what is the probability of finding an electron is given by this probability density. Okay. Now if this is a nucleus, I am drawing here a region I am considering. This is a region. In that region, what is the probability of finding an electron? That is nothing but what is the probability distribution of electron in this region. What is the third graph I am saying? Probability distribution. So that is taken here as phi pi r square psi square, here r, psi square dr and r. Okay. So now here in this y axis also r is involved, in the x axis also r is involved. At origin we know it will be 0. So whatever the graph, r is equals to 0 means initially, so graph should be starts with 0 origin right now. So it comes from here like this. Okay. So that's why I have some graphs here. If you look at these graphs, so for 1s also it will be starts from here like this. Is there any radial nodes here? Any nodes are there? No. What I told you, starting and ending point, don't consider them as nodes. In between them you consider. Okay. So this is for which orbital now, tell me? S orbital. But which S orbital? 1s orbital. This is for 1s orbital. Why 1s? Radial nodes are, like total number of nodes are 0 for 1s. Okay. So now look at these. I am taking here 4 pi r square psi square dr here, and here I am taking radius r. Okay. So now I am drawing a graph like this and positive. How many nodes are there? One node here you are seeing right now. So which means again it is starting from here. So it means I can say this is one node, and one node means definitely it will be either 2s or something like that. Because how many nodes we got for that? 2s. 1. So I can say this is for 2s. Is that clear or not? Now, sir, what about in the case of p orbitals? So I am saying 2p and 3p I am saying. So if I want to draw a graph psi versus r, how we will be drawing this? So look at this, how we are drawing this p orbital here, something like dumbbell shape now, but s orbital we are writing like a spherical. Okay. So if this is the nucleus, see this lobe is nothing but that is like more the sign means more the like more the lobe like this amplitude means I can say more is the probability of finding electron or more electron density you can say. So at the nucleus or close to the nucleus, probability of finding electron is minimum, but as we move away amplitude is increasing, so probability will be increasing. So at the nucleus, at the starting point it will be minimum or 0. So it means it should start from here, so it should go something like this. Is this clear or not? Okay. So for 2p, how many radial nodes are possible? Radial nodes n minus l minus 1. How many? 2 minus 1 minus 1, 0 na? So 0 radial nodes. This represents what? 2p orbital, like psi 2p orbital. Okay, so for 3p how should I draw? Tell me fast. Psi 2p for r. 3p I want to draw. So tell me fast. So just this should go like this, right now? So here it is one node. So how many radial? First find radial nodes for 3p. So n minus L minus 1. So n is 3 minus L is 1 minus 1. So 1 radial node you got. So this is that radial. Is that clear or not? If you want to draw the same for psi square, for this 3p. So you just need to write like this, yes or no? Place. So this represents one node. Is that clear or not? Yeah. So now based on this, will you answer these two questions? Answer these two questions fast. Tell me, which are the following corresponds to one node? One node, yes. Here only one node. Just looking how many times it is touching the axis, x-axis. That's it. That gives. Here how many nodes are there? Two nodes. Here how many are there? 0. Okay. It means. So can you tell me which orbital this graph is representing? For this particular question, we got option 2 as our answer. That is over. Extra question I am asking here is this graph representing which orbital? Starting from maxima and having 0 nodes. So maximum will start only in case of which orbital? S orbital. Okay. So this is S orbital with 0 nodes. It means 1s. That's it. Is that clear? This one starting from maxima and having 1 node. S orbital, maxima means, but how many nodes are there? 1 node. So it means 2s. That's it. Okay. Again starting from maxima having 2 nodes. It means starting from maxima 3s. That's it. Clear? Yeah. This one last question, then we'll move forward with few more topics. So tell me fast. Which of the following graphs corresponds to one radial node? One radial node. Yes. One radial nodes here only. Okay. That's it. And which orbital it is? If I ask. 2s. That's it. Simple. First one. 1s and third one 1 2, so 3s. That's simple. Yeah. Next we will be seeing the electron field. It might be P or it might be D or it might be F, because by relative comparison only we can say. See, as P2D, D2F if we increase, so what happens is this amplitude, like this curve is there na here, this upper curve is there na, that will expands. So more width means that is towards F, more sharp means that is towards P. Remember that point. Okay, by relative comparison we can say which orbital. Either it can be what is the minimum one with 0 nodes, means either it can be 2p or it can be a 3d or it can be a 4f. These are the thing. What is the minimum p orbital we have? 2p with 0 nodes. Okay. After that for d we have starts from d. Which d? 3d. And for f it starts from 4th. So 4f. So it can be any of these, but as number increases, that f like L value increases, width increases, broadness becomes more. Okay. Yeah. Next. So now we need to study about this electronic configuration. Like we have studied like quantum numbers now. Now we need to fill the electrons in those orbitals. Okay. So for that we need to follow some principles or some rules. So first one is what? Hofbauer principle. So according to these, electrons are filled in lower energy shells, lower energy levels first, or before filling the higher energy. First we should fill in lower energy. Now how can we identify lower energy and higher energy? Just we have did questions also. How can we identify? Bohr-Bury rule is there now. What is that? N plus L, and second one is N. If N plus L is same, just find L. Look at the L N value. That's it. Okay. So I have 1s, I have 2s, have next 2p, 3s, 3p, next 3d, 4s. I have something like this. Tell me, first electron enters into 1s because it is the lowest energy. After that 2s. After between these two 2p higher energy. Between these two, which is first electron enters into 2p. After that only 3s. After 3s 3p. After 3p, yes. Look at here. So look at the value of N plus L here. 3 plus 2. 5 here, 4 plus 0. So which is smaller number? 4s. So you should rearrange this. So after 3p you should fill in 4s, after that only 3. Remember this. Filling will be this manner. Removing is normal only. Filling first should be filled in 4s, then 3d. If I want to remove electron, we should remove from the highest n value. Which is having highest n value? That 4s should be removed first. See, filling of electron should be followed this manner. See, first 1s, next after this 2s, after this 2p, next 3s, 3p, 4s, 3d, 4p, 5s. See, after 4s only we got 3d. Just if you get confused anytime, just take its n plus L value and n value, you just compare, you will get the answer. That's it. Yeah. Let us move forward. Yeah. Next. This is what Hofbauer principle got over. Next one is Pauli's exclusion principle. So what he says? What? Once again? So we have 4 quantum numbers. So for a particular element, no two quantum numbers should be same. At least one should be different. Okay. So just look at here. An orbital can have maximum of 2 electrons, and these must be have opposite spin. Okay. For example, if they have same spin, what happens? Their spin quantum number becomes same. It should not be same. At least one should be different. Okay. So that's why either you can fill like this or you can fill like this, but you should not fill with the same spin. Okay. This is incorrect way. This is the perfect representation. Okay. So next one is Hund's rule of maximum multiplicity. So when electrons are filling in a degenerate level, degenerate means same energy level, degenerate level, electrons should be filled with maximum multiplicity. Means what? Multiplicity maximum means, for example, I have s orbital, so there is no issue with the s orbital because only one energy level, like one box only I can fill like this, and next electron I can fill like this. But if in the case of PD, in case P we have 3, so I have P like 3 electrons I have, P3 electronic configuration is there. Where we are? P3 electronic configuration is there. So you should fill one here, one here and one here, like this. They have maximum multiplicity. And if instead if I fill like this, is this correct? Is this correct? No, this is not the correct way. Only this way is correct. Okay, so I am saying a word maximum multiplicity. What is that maximum multiplicity? So the spin should be maxima. See, spin multiplicity S, or total multiplicity I can say is equals to 2s plus 1 you take. Okay, so what is this? How many spins are there? Each electron with half plus half. All of them are having same spin now. So 2 into 3 by 2 plus 1. So 4 you got. So 4 is a multiplicity. In this case 2, see these are having opposite spin. So half opposite spin means plus half minus half cancel out. We have with this one electron we have half. So total spin is 2. This is only doublet 2. But here we have quadret 4. So which is maximum? 4. So that's what you should follow, maximum multiplicity rule. Okay, is that clear? Okay, so always remember fully filled electronic configuration is more stable due to its symmetry. Electrons are fully filled now, so due to that symmetry it is more stable. After that half filled electronic configuration is more stable due to its maximum multiplicity. Okay, so for d orbital, what are the stable electronic configurations? Tell me for d orbital, for d subshell. D subshell, what are the stable electronic configuration possible? D subshell. See D, how many orbitals are there in D subshell? 5. Okay, so each orbital can be filled 1 electron, so that we will get D5 configuration, that is half filled, and full fill means D10. So these are the stable electronic configuration. Fully filled is more stable, after that half fill. Is that clear? Okay, this is due to symmetry and this is due to maximum exchange energy I can say, or maximum multiplicity I can say. Is that clear? Now write for carbon, what is the electronic configuration you can write? Atomic number is 6. So 1s orbital we have in the first shell, and next 2s you have in the second shell, and 2p you have in the second shell. Right now these are the possible orbitals in second level. Okay, do we have 2d? No. How to get whether 2d is there or not? Just take n value is 2, then L can be 0, 1 only. It cannot be 2. So 1 means P, 0 means S. That's it. Okay. So here 6 electrons. So fill 2 here. Each orbital can accommodate maximum 2 electrons. So 2 here, and here also 2. And what about this? This is a P subshell. In that subshell, how many orbitals are there? Its L value is 1 now. So 2L plus number of orbitals are there. So 2 into 1 plus 1. So 3 orbitals are there. Like minus ML values like minus 1 to plus 1. Like minus 1, 0, plus 1. Like 3 boxes we are writing now. So how many electrons you can fill? Maximum in p orbital? 6. Maximum 6. Out of this atomic number 6, 4 electrons got over. How many are remaining? 2. So fill that 2 here. If it is also 3 more, there is no electron to fill 4 now. Yeah, more 4 can be filled here. So that will be seen in the case of neon. Tell me. 1s2, 2s2, 2p6. That's it. All electrons are filled here. Yeah. So now represent them in the orbital representation. Give their orbital representation for this carbon first. So this is 2s, 1 box. This is 1s, and this is 2. So 2 electrons should be with opposite spin, and this is also, these are degenerate now. So you should fill 1 electron. Okay, is that clear? Now tell me for oxygen. 1s2, 2p, 4. Okay, and tell me orbital representation. 1, 1, 1 and last one will be paired. Is this clear? Yeah. So now look at here. This is over now. Now tell me for scandium. Scandium atomic number? (21). So tell me, how can we write? Argon. Argon means 18. Okay. 18 over. Next. Huh? After that? So better don't do this first. Write everything. Tell me. Like start from 1s. Because you are struggling. So I want from basic. Yeah. So tell me from starting. 1s2, 2s2. 2p6. 10 over. Next. 3s2, 12 over. 3p6. How many? 18 over. After that. 4s2. Yes. So 3p6, 18 over now. So argon 18 over. After that 4s are 3d. 4s. We just now discussed. 4s, 3d. So 18 over. So 2 here. Next 3d, 1. Like that. Is that clear? Yeah. If I want to remove one electron, from where I should remove? 4s first, because higher n value, no? From there you remove. Okay. So now see here in the previous case I have explained this. See this, what is the highest n number here we have? Principal quantum number n? 2. N equals to 2 is highest. So during the chemical reactions, this highest n value is there now. So those orbitals will involve in the chemical reactions. We are calling them as valency electrons. What is that? Valence electron. How many valence electrons in carbon? Like just valence electrons, how many are seeing here? 2 plus 2, 2 plus 2, 4 now, that will be your answer. Okay. So now in oxygen you say? 6 are there. So this 2 plus 4, 6 valence electrons. Okay. Yeah. Next, I am giving you vanadium. Tell me. Okay, tell me. So remember, scandium, titanium, vanadium. So scandium means 21 you are saying, titanium 22, vanadium 23. Okay, so just tell me what I should write. Argon 18 over 4s 2, 3d 3. Simple trick I will tell you. Look at their electronic configuration. 23 now. So 4s 2 put here, 3d put here. These numbers only you are writing here. Okay, this one you tell me fast. Argon over 4s2, 3d 2. This is just simple trick I am saying. Okay. If I want to write for chromium, then chromium is 24. If you follow this trick, 3d 4. This is wrong. Okay, why it is wrong? Tell me. Because this, if I fill one electron from here to here, it get half filled electronic configuration. That's why it becomes what? So 4s1, 3d 5. Okay, this is exception because of half filled configuration. You can remember like this. 1, 2, 3, 4, 5 like this. Okay, instead here if you fill like this, having one vacant orbital, right now If I fill like one electron, maximum multiplicity is there, more stable. Okay, and next if I want to write for nickel, 28. 4s 2 3d 8, that is perfect, no issues in this case. Again you will see one more exception in the case of copper, it is 29. Tell me. 4s 1 3 see, instead I am filling 4s to 3d 9. If we do in this way, 4s 1 3d 10, this is perfect, again due to fulfill electronic configuration of d orbitals. Okay, yeah, so these are the two things you should remember in the case of 3D series or 3D series elements. Okay, like, okay, yeah, is this clear? Now I am writing nickel plus 2, from where I should remove electrons? 2 electrons from here, so it becomes 3d8 4s 0. Is this clear? Now I am writing iron plus 3, this is 26. So tell me, what is the electronic configuration and how many unpaired electrons are present? 3d5. So first you write 3d6 4s 2, removing 3 electrons now, it becomes 0, and from here also 1 electron should be removed, 3d5. So how many unpaired electrons are there? 5. Like you can represent that in the 5 orbitals, 1 electron, and magnetic moment value if they ask, mu is equals to root over n into n plus 2 Bohr magnetons, I told you while studying spin magnetic moment. So 5 into 5 plus 2, 7 into 5, so root 35. So 35 means nearly equals to 5.9 you can take Bohr magnetons. Okay, around. Okay, so now if I ask for Fe plus 2, fast. What is electronic configuration? 3d6 4s0, so 4 unpaired electrons, that's it. Okay, so just go through this over. Next, and zinc, you tell me. Zinc 30, it means 30 means what? 10 4s 4s2, that's it. Okay, yeah, this is about electronic configuration. Okay, next what we have here, yeah, so almost all discussions are over related to this, and if you are having any doubts you can ask me now, or do you have you taken okay, yeah.